Being in the equipment industry, we were constantly fighting companies in Korea and more recently in China that were being strongly supported by their customers in Korea and China. And the attitude in the US was, oh, I can buy it from Asia, so I don't need to do it here. We need to build the digital twins for our fabs, our factories, before they do. The first time you build it, it's not going to be very accurate. It gives you an environment to learn in. They spend 20% of their time solving the problem to 80% accuracy and 80% of their time trying to close that gap. And that 80% of the time is not rewarding because they don't understand what's going on. Let the humans start, let the machines finish. It's a great marriage of human-machine collaboration. Apple's now in a very precarious position. They're very, very strongly dependent on what's happening in China. How do you get out?
Anyways, hey, Rick, thanks for joining us here on Micro Journeys. Pleasure having you on the podcast here.
It's my pleasure.
An interesting journey that you've taken. I'd like to start kind of at the beginning here. You got your undergraduate over at Penn State and then your PhD over at MIT. What got you interested in the world of science and technology?
Well, I think I've been interested in science and technology since I was a little boy. And I was just kind of curious about why we're all here. What's the nature of the universe? And so that naturally drew me to trying to answer some of those questions, even in elementary school. And I remember very distinctly when I was first introduced to the periodic table of the elements and the Pauli exclusion principle. I think it was in 5th grade. And I just thought, wow, that's so cool. That explains so much. And so my interest in science and technology kind of started from that early age. My father was a chemical engineer, so that had some influence on me as well. He was a biochemical engineer in the tobacco industry, which didn't particularly appeal to me. When it came time to go to university, my father convinced me that it didn't really matter which school I went to. And we were citizens of Pennsylvania, so Penn State University was attractive to him from a financial point of view. And he said, you just want to go to a big university where you have lots of choices. Because even though I was interested in science and technology, I wasn't quite sure what I really wanted to do. And so I enrolled in the College of Liberal Arts at Penn State. Initially, I was interested in psychology. But after I got a B in the course, I'm a bit of a perfectionist. So and at the same time I got a B in my freshman psychology course. I shortly thereafter taken a course in social psychology, and I was really enamored with that course because they were reviewing lots of experiments on people, and they'd put people in stressful situations and measure their responses. I thought, that's really cool. I want to do experiments on people. So I declared my major at the end of my freshman year to be sociology. Shortly thereafter, I think it was in the middle of my sophomore year, I got really bored with the sociology curriculum. So the initial course I took where they were doing experiments on people seemed to be replaced by essays. I remember there's a famous book, I think it's by a guy named Piaget, about the psychology of the child. I'm sure if I were to go back and look at that now, that I would have a much greater appreciation for what was written. But at the time, it bored me to tears. And I became increasingly unhappy and struggling with what I was going to do. And one of my roommates was a big science fiction fan, and he introduced me to Isaac Asimov and the Foundation trilogy, which just blew me away. I was really excited by that. And about the same time, and I've struggled in vain for years to find this article, but what I remember was an article in Scientific American by Isaac Asimov entitled Science Fiction, the Only Relevant Literature, or something to that effect. And the idea was, Asimov actually wrote historical books as well. I think he had one on the rise and fall of the Roman Empire, for example. And his Foundation trilogy is actually based loosely on what happened with the Roman Empire in some respects. Science fiction being the only relevant literature because it talks about what's going to happen in the future. And you imagine the future. And if you think about technology and where it is today, a lot of it was predicted decades or if not centuries before by science fiction writers. So I, in my mind, said, I want to be a science fiction writer. I made my decision. But for me to be a good science fiction writer, and Asimov emphasized this, you have to know science. I wanted to write science fiction that was believable and realistic and might actually come true someday. So I made a decision to switch my major, and this was 1972, I think. And nobody went from the College of Liberal Arts and the Humanities into the College of Science. Everybody tended to go the other way. They found science much harder, the math much harder. And so when I applied, and I interviewed with professors in the Department of Chemistry, I was interested in chemistry. Again, my father was a chemical engineer. In high school, I took advanced placement in chemistry and did very well at it. I liked chemistry. I took an advanced placement test at Penn State, so I exempted freshman chemistry. So I had a head start in chemistry. I requested a transfer into the chemistry department, College of Science. And make a long story short, they eventually accepted me. And then I had to cram because I had used up essentially all my electives on all my social science classes. And I never took calculus in high school. So I was I was going to summer school, taking a full load. I always felt a little bit deficient in electricity and magnetism as a result of having spent my first year and a half or so at Penn State in the liberal arts college. But it all worked out well. I had some really fantastic professors. I tell people all the time, my 4 years at Penn State were some of the happiest years of my life. It's a fantastic university, fantastic setting. And I'm a big football fan. So
yeah, they don't lack in that department.
They don't lack in that department. And I'm a big fan of Joe Paterno and the whole Penn State program and his commitment to the student athlete and his value system around education. So he's always been a role model for me. And we won't get into the scandal. I think that's we won't get into that.
He was a very good coach. He won a lot of games. Yeah.
He's still a hero in my eyes, and I'm still a big fan of his. And I'm a big fan of Penn State. I'm involved working with them in a number of capacities now. So then after I never got a B in the sciences or the math at Penn State. So I was in pretty good shape after taking my GREs was lucky enough to get into MIT, into the graduate program. By that time, I had decided I liked physical chemistry because I liked physics more than synthetic chemistry. And so I gravitated towards that area. I was fascinated by lasers. Lasers in the early 70s were a fairly recent invention.
They were all the rage.
But they're actually, it was interesting. The application of laser technology was still kind of up in the air, other than using it for welding and cutting. And remember the James Bond movie, I think in the early 60s with Goldfinger and the scene with the laser that really left a lasting impression on a young kid like
Tying back to I want to write science fiction.
Yeah, science fiction, but I was also fascinated by physics and laser technology and optical spectroscopy, and I like bright lights and colors. So I ended up doing undergraduate research at Penn State doing laser spectroscopy. It was a failed experiment, but nonetheless, I got some exposure to laser technology. And then when I went to MIT, I pretty quickly decided to work with a professor named Robert Field, who was an assistant professor and was focused on laser spectroscopy of small molecules. At that time, while I still had this idea in my head, I wanted to be a science fiction author someday, I was pretty enamored with the academic scene, and I thought, well, I'll start out my scientific career as a professor. So I'm going to work for an assistant professor and see how it's done. And that turned out to be a really good decision because it convinced me I didn't want to go to academia.
Yeah,
because he was short on funds all the time. I was his first student. My first job was, he got a big laboratory in the basement of MIT, right by the Charles River. not that you could see the river because we were in the basement, and I walk in and it's just full of junk from the previous professor who didn't get tenure. So my job was to clean the place out.
How about that for our first research project?
Well, it gets worse because back then, computers were relatively new also in the laboratory. And most of the people around us had PDP-8s and with paper tape readers and things like that. But he had no money to buy a computer. They're a lot cheaper today than they were back then. We would do our spectroscopy using analog equipment, which so you'd get your signal. Basically, you're measuring a spectrum, and you're measuring intensity of the light as measured from a photomultiplier tube, which is a current source, goes through an electrometer that puts out a voltage that goes to a recorder. And what you need is a strip chart recorder. So time is one axis, and your intensity of the radiation is on the other axis.
And you're looking for those peaks in the energies because those peaks will give off the signals of the actual...
Tells you the structure of the molecule. Yeah. So from the analyzing the spectrum, you can determine the electronic and structure of the molecule, the vibrational structure of the molecule, rotational structure of the molecule. And but he couldn't afford a strip chart recorder. And I found in all that pile of junk what's called an XY recorder, where you've got it's just two servo motors, and you're plotting X versus Y and something, and that's totally inappropriate for application. So he says, okay, your first project is turn that into a strip chart recorder. I didn't know that much. I didn't have that much practical experience doing stuff like that. But I tore it apart. There were some guys next door in the electronics shop that helped me a lot. Ray and Murray, I think they were, not the radio show, the Click Clack brothers. They reminded me of the Click Clack brothers, who were also in Boston, and I think they went to MIT as well. But anyway, so they helped me, but I had to change the gearing, and I had to pull out the servo motor and replace it with a clock motor. And I got all that to work. I was feeling really good about it. I couldn't get the pens to work. The pens kept clogging. So finally, I found a jury-rigged felt tip pen. I got it all to work. And about a day after I got it all to work, my professor comes in and says, "Great news, I got a grant. Now we can buy a strip chart recorder." So anyway, we built our own lasers. We bought an argon ion laser, which pumped a dye laser. We built the dye lasers, and we built we were doing spectroscopy on small metal oxides, barium oxide, calcium oxide, strontium oxide, funded mostly by the Air Force for reasons that still escape me, but it was fun, although I struggled to understand what impact it would have beyond my education. So we built everything ourselves. And I remember he had taken the design of the dye lasers from a group at Santa Barbara that he did a postdoc with. And we built them. We built two for our lab, and we built one for David Pritchard in physics. And we could never get those dye lasers to perform very well. They were always kind of on the verge of lasing, and the power was low. And so the experiments were very, very torturous because the signal to noise was low. And we could never figure out why they were so bad compared to what he had used in Santa Barbara. We even brought people in from Santa Barbara. We were comparing notes. And that went on for the better part of 2 years. And it's just a real chore. And one day I'm in the lab alone, and almost nothing ever happened until 5 p.m. or later. It was interesting. The electronic noise, and we had a lot of signal to noise because the lasers weren't stable, was always higher during the day. And at around 5 o'clock, everything quieted down as most people went home. So I typically would start my work at 4 or 5 in the afternoon, and I'm sitting there tuning up the laser and and I just look at dye jet, and there's something called Brewster's angle. And if the pump laser comes in at Brewster's angle, the reflection is minimized for the polarization that you're selecting. So it maximizes the probability for absorption of that polarized light. And I'm staring at this thing, and I'm like, oh my God, that's not at Brewster's angle. That's at 90 degrees from Brewster's angle. Probably a dozen people looked at this with experience for years, and nobody noticed that. And so I just took a wrench and I rotated it, and my power meter went whomp right off scale.
All the way, oh, wow.
And so I became a bit of a hero because everybody benefited from that realization. But that taught me a big lesson that, it's, you got to question yourself and all your assumptions all the time. It's so easy to get trapped in this little world and miss something much bigger.
That was your moment. That could have been the Gaucho effect. You could have, said, look, if you just twist it just this little bit, now you get your power meter to go.
Right. And it was for me as a second year, third year graduate student, I still lacked a lot of confidence. So that was a real confidence booster for me as well. And so I did a lot of work as an undergrad. My thesis is one of the longest probably in MIT's history, because I decided, I'm a big believer in the scientific method and providing enough information for anybody to reproduce what you did. And I was not only doing experimental work, I was doing computational work. And so I put all my programs into the thesis and all the raw data.
Your thesis is about this thick of...
It came in 2 volumes.
Oh, no way.
And may still be the long, but it's, the real content or prose, if you will, is only about 100 pages. But I remember going in for my thesis review, and the chair of my thesis committee was Professor Robert Silby, fantastic professor, great teacher. He slaps my thesis, both volumes, down on the table, and he says, "I've never seen so much verbiage in my life." And then they proceeded to grill me on everything. And I kept answering the questions, and I didn't have the nerve to do what my best friend, a guy named Craig Jensen at the time, did. When he went into his thesis committee about a week before mine, he brought in a bottle of whiskey and poured everybody a drink. But
that's funny.
I hadn't done that. And so they were peppering me with questions. And finally, I don't remember what the question was. I just said, I don't know the answer to that. I'd have to research that or look that up. I said, finally, we're done. You admitted you don't know everything. So, and
that's a good thesis review, right? I mean,
no complaints.
Where your panel's sitting there, they grill you for a little bit. Then there's that moment of, okay, now we can kind of, tease you a little bit.
And I knew it was somewhat pro forma, because the real litmus test in getting your PhD in the chemistry department at MIT back then was the oral exam and your thesis proposal that you made after a year and a half. And that's where they tend to flush people out who they don't have confidence in. And I had passed that. My toughest question in that one was I'd apparently misspelled the word elegant. Don't ask me to spell it right now. And one of the members on my committee, Jim Kinsey, who is also a fantastic professor, really inspirational for me, just asked me, well, how do you spell elegant, Rick? And so I spelled it the way I'd spelled it in my written document. So he knew it wasn't a typo, and I got it wrong. He says, no, tell me how you spell elegant. And I realized, okay, it must be wrong. So I spelled it again, wrong in a different way.
Oh, boy.
So again, until I got it right, they didn't pass me on the oral, but otherwise I passed the oral. So the thesis review was somewhat pro forma.
Is your thesis something that can be found online?
In fact, I recently I lost my original copy. I lent it to somebody, and I don't remember who, and I never got it back. So I have a pretty bad, ratty photocopy. But I recently went online to MIT and was able to download in PDF format the whole thesis.
Well, we'll want to put that in the show notes. See if we can get the both volumes.
Yeah, I started to reread it. It was painful.
There, a little side note: they have publishing companies where you can just send in your PDF and they'll bound it, and then they'll make sure it's all hardbacked and all that kind of stuff. So,
but the bottom line was I did a lot of work in the thesis, so it was also a compendium of a lot of publications. I think I had about 20 publications by the time I got my PhD in 4.5 years. But they were all on kind of isolated studies of this molecule, that molecule. Some of it was based on my experimental work. Some of it was based on things that were in the literature. Some of it was based on collaborations we were doing with researchers in Sweden and France. I spent some time in France doing quantum mechanical calculations of molecules. And so but there was no single big driving question, which left me unsatisfied, frankly. And I felt it convinced me, that whole experience convinced me I didn't really want to go into academia. also didn't have the confidence I'd fare well in academia, and left me searching for something that was more meaningful, had a big influence on where I went next.
Yeah. So after you got your PhD, your transition was over to Bell Labs, correct? And was it connected to some of the work you were doing? Because
Yeah. So actually, I did a postdoc for a year in the physics department at MIT, doing molecular spectroscopy. That was with a guy named Dave Pritchard, who many years later mentored a guy named, I think, Ketterle, who won the Nobel Prize for studying Bose condensation, very cold atoms that are made very cold and trapped using forces from laser fields. And at that time, they were pioneering the formation of exotic molecules like sodium argon, sodium neon, a rare gas bound to a very reactive alkali atom. And they would do that through a molecular beam. So they'd heat up the sodium, vaporize it, and train it in argon, blow it through a small nozzle, supersonic expansion, everything cools down, and then hit it at right angles with a laser. And it's a very sodium neon, sodium argon, a very strong absorber and very bright emitter. We were doing laser-induced fluorescence, and I was the molecular spectroscopist. So I was brought in analyzing all the data and running those experiments. That was a great year. But again, it left me dissatisfied. It's like, it's really interesting physics and it's fun, but I couldn't connect to practical applications. And I had this bent to do that. During my course at MIT, one of those many projects that ended up in my thesis was I was doing some work with two Bell Labs scientists in the Francis Bitter National Magnet Laboratory. And so we were doing magnetic spectroscopy. Didn't involve lasers in this case, but we had a glow discharge that would run inside or I guess it's the effluent from a glow discharge in a very, very strong magnetic field. That's why back then it was the National Magnet Laboratory, which since moved to Florida. And so I got to know the Bell Labs guys, and they got to know me, and so they invited me down to Bell Labs while I was a postdoc, and I interviewed there, and they ended up making me an offer. One of the things that appealed to me is they talked to me about this new technology that had just gone into production to make semiconductor chips. I didn't know anything about semiconductors or how they were made at the time. Most people didn't. That was called plasma etching. And they said, nobody understands how this stuff works. And with your background in molecular spectroscopy, I mean, these plasmas are glowing and radiating and telling you what's going on inside. We think you'd be a good match to just study these things and understand them, because the Bell Labs perspective was they took a holistic view on all technology. They wanted to understand deeply the mechanisms at play so that they could use that knowledge to make better reactors or better devices. Back then, that was 1980, basically everybody in the semiconductor business was vertically integrated. And AT&T was no exception. AT&T, Western Electric, built their own equipment, built their own plasma etchers, built their own e-beam writers for mask production, made their own masks, own lithography equipment, you name it. It was all built in an equipment division of Western Electric. I was in research, so I was indirectly supporting those guys, and I had the freedom to kind of just follow my curiosity. And so I set up a lab and built my own reactors and started to do laser diagnostics on them, and started to map out the motion of ions in particular in these reactive plasmas as a function of where they were between the electrodes. So what happened to them as they approached the surface that you were etching. And then also these are radio frequency discharge. So I synchronized the firing of my laser to the RF field. And so I can map out space-time. I created space-time maps of ion motion in these plasmas. And that,
and how much intensity is needed per, depth of etch and stuff like that. I'm assuming that was part of a characterization you had within this?
Yeah, I was also doing some etching and trying to connect the two, but there was actually surprisingly little known about radio frequency plasmas and radio frequency plasmas through reactive gases and gases. I was looking at boron trichloride plasmas and chlorine plasmas and things like that.
Why don't you describe what that is a little bit for the listeners? Why would you go with a radio frequency?
So the radio frequencies are used because you're trying to bombard the silicon wafer and etch, let's say, silicon or silicon dioxide or aluminum. You're trying to pattern it or transfer a pattern that was defined lithographically. Back then, it was ultraviolet light in a photosensitive polymer that would be exposed and then developed, and you're left. That creates a mask. Now you have to transfer the mask, let's say, into aluminum, and so the mask is on top of a plain deposited aluminum film, and you're trying to create the lines, the conducting lines that's going to connect one transistor to another. That's a typical plasma etching. And so boron trichloride chlorine mixtures were found to be very effective at etching aluminum. Boron trichloride is critical because aluminum makes a native oxide, and the boron trichloриde's effective at breaking through that. But nobody really understood, was it chlorine atoms doing this etching? Was it chlorine ions? What was the role of the boron trichloride? And the key to plasma etching, the reason plasma etching had recently been introduced, before that it was all wet etching. But wet etching, in most cases, occurs isotropically. In other words, the etch rate is equal in all directions. So you want to etch down, it'll also etch sideways. So if you imagine a mask, and imagine the mask is a rectangular shape, and you want to transfer that pattern with high fidelity, you want vertical sidewalls. So you want fast etching this way and no etching that way. That's the ideal plasma etch. And that's what was happening by and large, but nobody really understood why. It turns out it has to do with the transport of the ions to the wafer, which is the ions are largely moving this way towards the wafer, and they enhance the natural chemical etching. But because the ions don't go this way, they don't enhance the etching that way. That's how you get anisotropic etching or vertical etching.
So to simplify it, it's almost like you have a cake, right? And you can either cut the cake with a knife, which would be your plasma etching,
yes,
or you can cut the cake with a spoon, which is going to carve out
that's a great analogy.
Massive portions of the cake, right?
That's a great analogy,
yeah.
Right.
So,
but back then, actually, there's some really beautiful work done at IBM by Coburn, Winters, and Kay, and they use molecular beams where they alternately expose the wafer with an argon ion beam and then a neutral beam of xenon difluoride, which was a proxy for fluorine atoms. And then they would expose the silicon to both beams at the same time. And they found that the etch rate was dramatically higher, like 10 times higher than the individual etch rates with just argon ions or just xenon difluoride. That's called the ion neutral synergy. That's the basic mechanism. And that was published in 79, I believe, but it wasn't widely known and not everybody accepted it. But my studies were more about, okay, we know ions are important, or we think ions are important. So what are the ions doing in these RF discharges? How do these radio frequency fields affect their transport and their energy distribution? So the current and the energy with which they impact the surface, and that will determine the etch characteristics. So I made a bit of a name for myself with those experiments because nobody had done experiments like that before. And I then proceeded to invent a technique to measure the electric field, which is responsible for accelerating the ions. And I used a spectroscopic technique called Stark mixing. If you put molecules in an electric field, depending on the state of the molecule, it reacts with the field in a different way. And you can, there's...
No, when you say the state of the molecule, are you talking about this from like a metal alloy perspective?
Is no, this more of these are, so the molecule I used initially was boron monochloride that's formed in the dissociation of boron trichloride in the plasma.
Okay.
So it's a diatomic molecule. By what I mean by the state of the molecule is it has different rotational, vibrational, and electronic states.
Mm-hmm. The
interaction with the electric field is a function of what electronic state you're in and really what rotational state you're in. The vibrational state's, I think, a little less important. And so how that's manifest when you look at the light coming out, or in my case, I'm inducing absorption of that boron monochloride from a ground state to an excited state, and then monitoring its fluorescence back down. The fluorescence that comes out, depending on what I excite, changes in the presence of an electric field. There are so-called forbidden transitions based on quantum mechanical rules that are broken when you apply an electric field. The rules change, if you will. So transitions that are normally forbidden, you don't see anything, suddenly become allowed, and they literally steal intensity from the allowed transition. So you can monitor an allowed transition and a forbidden transition, and what you'll see is the ratio will change depending on the strength of the field. And that's the technique I used. Now I could map out not just the motion of ions as a function of space and time,
And
but
this
the
is all
electric
done
fields.
through spectroscopy.
All done using optical spectroscopy in a non-intrusive way.
Interesting. So the way I'm interpreting what you're saying here is you have some kind of light, right, that is coming in, and you're measuring the reflection associated with it, and any change in characteristics of that, whether it be a change in the phase of the light, a change of the energy of the light, and that's all dependent on how the molecule A you're measuring, so you know what energy that's going to be, but also an orientation shift. And that orientation shift will give subtle characteristics of the spectroscopy that you're doing to see how that is changing with the electric field, right?
Yeah, it's not so much an orientation, it's just the presence of the electric field, because the molecules are rotating, they're tumbling all around.
Mhm.
So the orientation relative to the field is kind of averaged out in that respect. But there's still an electric dipole that interacts with the electric field that causes this change in the quantum mechanical rule.
And the reason that this is important is because as you're doing your etching associated with, your manufacturing, you want to make sure you have it in the most, pristine status or state for that etch to take place, correct?
Yes, that is correct. But back then when I was doing this was just, again, I'm following my nose, what's interesting, what's curious, and nobody had made these kind of measurements before in this kind of environment. The electric field's critically important because it determines the energy with which the ions hit the wafer to do the etching, and that energy, it also determines the angle at which the ions hit. So mapping out the fields, and then mapping and also mapping out the motion of the ions as they go into that boundary layer between the plasma and the wafer is all critically important. Now, what I generated, I think, was a lot of qualitative insight. It gave me a deep intuitive understanding of what's happening in those plasmas. And as I published my results, I shared that deep intuitive understanding. That helped promote my career. I started to get a lot of invited talks and so forth and so on, published a lot of papers. It still left me dissatisfied because I couldn't draw a straight line and connect the dots from these kind of basic experiments and this basic understanding. I'm also trying to model all this stuff to interpret in terms of the basic plasma physics. Just collaborating with people to get that done. Much harder then than it is today. But I couldn't draw a straight line to, okay, we need to change this reactor design in the following way to get more vertical etching or higher throughput or longer time between cleans on these reactors. That was still a very tenuous connection. At best, there was a qualitative feeling for what you might.
And this is one of the pieces that I was curious about, because what you're describing here is a lot of R&D work, right? And in the semiconductor world, transitioning R&D to full rate production is a very challenging thing to do.
Correct.
Because it has to be done in a very repeatable process that doesn't increase time associated with any of the wafer throughputs that are going through, because longer time for wafer throughput, more expensive, less product comes out on the back end. So taking R&D, getting it to there, I mean, it may be very cool in the lab, but how is that going to help these coin operated companies, right?
Right. So again, it gave me, and I think over the years, a lot of other people, deeper insights and an intuition for what's going on in these reactors, but it didn't give me a formula for making a better etch reactor product. Moreover, AT&T uh, I think by my first publications on the electric field measurements were like 1984. But by the end of the 80s, AT&T was completely out of their own equipment business. And the AT&T, actually Western Electric factories, were buying all their equipment from Applied Materials, Lam Research, Tokyo Electron, Drytech, General Signal, all the equipment companies that basically cropped up beginning in maybe the mid 70s through the 80s, and they were gaining momentum all the time. And that happened because of economies of scale. There are a lot of semiconductor companies back then, hundreds compared to today. There's only really 6 of significance.
It's
about
smaller,
6 companies account for 80% of the production of chips. But back then it wasn't so concentrated. And for each company to be having their own equipment was just economically not viable. It just became a huge burden, and you didn't have the benefit of learning from lots of different applications, lots of different customers, frankly. So that was the value proposition of the equipment companies. I had also gotten into management at Bell Labs. In '88, they promoted me to department head, and I ran a department that was mostly focused on advanced packaging, which was interesting. Way ahead of its time. Way ahead of its time.
What was advanced packaging?
It was silicon. It was flip chip technology, silicon on silicon.
Okay.
And AT&T called it advanced VLSI packaging, AVP. Okay. And they also
VLSI, very large scale integration.
Yep. And actually, AT&T decided to shut down the effort, originated in research and moved into development. And they decided to shut it down because it was ahead of its time and couldn't keep pace with Moore's law, which was just putting more and more transistors in a smaller and smaller area through what we call monolithic integration as opposed to advanced packaging. So it was arguably 30, 40 years ahead of its time. Now,
talk about Back to the Future, right? Because I mean, now you're seeing these big 6 that you're describing saying, hey, let's go reinvest in packaging capabilities that are vertically integrated. It's funny because you see some of these original ideas from a business perspective just come full circle.
Right.
Yeah.
And IBM had an advanced packaging module. They were ahead of everybody else back then, but that was a kind of a niche, small volume application. Bell Labs and AT&T shut down the development effort, but the research guys, and by that time we were headed by Arno Penzias, Nobel laureate for co-discovering the Big Bang. It was like, we're not going to give up on this. We think this is the right thing for the future. And so when they promoted me, they put me in charge of this department. The previous department head had decided, I think, to leave for academia. And so I fought a lot of internal battles to keep the thing going. And the development organization didn't want us to do it, but the manufacturing guys did. And we ended up doing advanced packaging, putting silicon on a ceramic substrate. And that went into what was at that time AT&T's flagship product for switching. And, they did everything, switching and transmission in the 5ESS switch. So I ended up being part of a team that transferred technology directly from research into manufacturing. Didn't draw much on my spectroscopic background or plasma background. In the meantime, at Bell Labs, as a department head, I still had to maintain my research efforts. I was still doing research on plasmas and doing plasma diagnostics and modeling and so forth. And then in '93, they came to me and said, displays are all important for the future of consumer electronics. And AT&T was developing a new video phone. I think it was certainly the second, if not the third attempt. The picture phone was the thing that was most famous back in the 60s. And that failed for a number of reasons, not the least of which was you need a critical mass. If I have a picture phone and you don't have a picture phone,
what's it worth?
What's
right?
it worth,
Yeah.
right? And the network bandwidth wasn't there. But AT&T decided to try again, and they came. You probably don't remember. It came out with this little phone, actually a desk phone with a very little screen, and the compression algorithms weren't very good, and the bandwidth of the network wasn't very good. So But at the time, they got all excited and they said, we have to own the display. In fact, the vision was the display will become the circuit board of the future. And so they launched a big strategic effort in flat panel displays. And again, AT&T had pioneered flat panel displays, and it started and stopped and started and stopped. So maybe against my better judgment and things that people told me, they came to me and asked me to lead the research department for this new effort. And I accepted. And I started from scratch and found Bell Labs was a wonderful place to find really talented, productive people, and everybody was excited. So I had no trouble building up a team very quickly. AT&T was collaborating with a company in Japan initially and ultimately trying to work out a deal with Korea. But the Japanese company, I guess I could say it was Matsushita or Panasonic. They just built a big factory in Ishikawa on the western side of Japan. And we had non-disclosure agreements of various sorts. We went out there, visited the factory. They opened up the kimono to us, shared the technology, and enabled us to come up pretty quickly. So we set up a prototype line. We started to build our own active matrix liquid crystal displays. We were doing thin film transistor fabrication. That opened up a whole new world to me, not just in terms of display technology. I learned a lot about liquid crystals, but I really learned transistor physics because I was running a group that was now making them. And it was a small team, maybe 20 people. And again, Bell Labs culture was, you're a department head, you're still hands-on. So I assigned my task as test technician. And I assigned myself to report to the lead device designer who reported to a supervisor who reported to me.
So you got this whole trifecta going,
right?
Yeah.
So it was really inverting the pyramid, which I think endeared me to my team. We had a really great team spirit. But I used to go in the lab. I did all the programming for the tester, and I learned how transistor works because I was there measuring everything all over the flat panels. But by 95, AT&T was struggling. It had, telecom had become very competitive. There was a consent decree in 1984 that broke up AT&T, so they were a smaller company now. And make a long story short, Bob Allen, the CEO at the time, decided that he was going to split the company again. And that's when Lucent was created. And Lucent basically took all the Western Electric technology. So all the hardware products and consumer products, which they basically killed off pretty quickly, went to Lucent. They had a few years earlier made a hostile takeover of NCR because they were desperate to get into the computer business, and their organic efforts had failed. But they kind of drove NCR into the ground. I was in the middle of that because NCR was pulling hard on new display technology for ATMs, not just video phones. NCR pioneered ATMs. So they decided to spin off NCR after spending $7 billion just a few years before, spin off Lucent, and then AT&T would just be a long distance service provider because the local companies had been spun off in 1984. And I decided at that point I had lost confidence in AT&T management. It was only a matter of time till they were going to lay me off. It didn't matter how good you were.
But it also seemed like it was a pivot from your passion, right? I mean, as a service company that AT&T was turning into.
I would have gone to Lucent.
Okay.
And I didn't have a lot of confidence in where Lucent was going to go. And most likely I would move to Orlando, Florida, which is where the latest semiconductor fab was. And I thought, well, if I'm going to uproot my family and move someplace, I'd rather move to California and Silicon Valley. And a lot of my colleagues had made that decision before I did and ended up at Applied Materials, Lam Research. I had contacts at Lam. I was enamored with Lam Research's technology, still am. And so that's why I made the jump there. And initially it looked like a really bad decision because Lucent just took off.
Yeah, they spiked pretty quickly.
And Lam 2 years after I joined, was 1 quarter from bankruptcy. Turns out that the Lucent performance was a bubble fueled by some questionable accounting procedures.
Interesting.
Shipping equipment, declaring it as revenue when it was really eval units for their customers. And then when the Y2, well, it was the .com bust around 2000. I mean, Lucent just kind of got wiped out. By that time, we were turning Lam around.
Interesting. So when you started over at Lam, I mean, because this is a pivot from the AT&T Bell related activities. What were you doing over at Lam to start out?
So I was excited about going to Lam because now I felt like with all I had learned about how these plasmas worked, I could be in a position where I could help make products. And I decided that the publishing papers was fun and getting the recognition, invited talks was satisfying, but not enough for me. I decided, the ultimate feedback is not how many times you get cited by somebody for something you wrote, but whether or not somebody's willing to pay hard cash for something you created. And it's unambiguous, and I really like that. So when I went to Lam, they wanted me to be a director of R&D in the CTO organization. Like, no, I've been doing that for the last 15 years at Bell Labs. I want to be involved in a business unit and make products. I want to jump into the fire from the frying pan, if you will. Well, I got what I wished. So I struck a side deal with the CEO and the president of the company. That
was it. David at the time?
No, that David Lam had been forced out as CEO after 2 years in 1982. This was in 1996.
Okay,
and he had left Lam, I think, by 1986 or 7 completely. So the company was run by the second CEO, was Roger Emmerich, and the president, Wei Tu. So I met with them and told them what I desired, and they said, "We hear you. Join as director of R&D, and we'll figure something out and put you in charge of a business unit." So I accepted the offer, started out in R&D, and after about 4 months, Wei Tu called me up and he says, "We're trying to break into high-density plasma CVD, and we want you to go over there and take a look at what they're doing because we're struggling." And
CVD, chemical vapor deposition.
Chemical vapor deposition. And high-density plasma CVD is a process where you're basically doing deposition and etching of, let's say, silicon dioxide, and you're trying to fill the gaps between these conducting lines that are connecting your transistors to insulate them, and then you're going to build another layer like that. And because of Moore's law, the gaps were getting so small that the traditional chemical vapor deposition, think about it as you got a fence you're trying to paint with a spray gun. And if the posts of the fence are very close together compared to the width of the fence post, and you're coming in from one side, or you're coming in,
you're going to spray
from the top,
you're going to hit,
you're going to spray the outsides, but you'll never get any paint on the inside. Well, that's the same thing with filling these gaps between the metal lines. You couldn't fill them up by conventional chemical vapor deposition because the deposition would just go everywhere. It would kind of seal off the top, and you'd be left with a big void.
Yeah.
But with high-density plasma CVD, you're putting down this film, and you simultaneously bombard it with energetic ions, basically etching. And so you're removing things at the same time you're depositing. It keeps the top open, and you basically get what's called bottoms-up filling.
Mm-hmm.
And the quality of the films is very good, too, because of all the ion bombardment. And Lam had purchased some technology from Sumitomo Metals. They had a deal with them called electron cyclotron resonance, which I had studied when I was at Bell Labs. I didn't like the technology. So they sent me...
What's the cyclotron portion of this?
So basically, your plasma is now inside a magnetic field, and that magnetic field excites a cyclical motion, cyclotron motion of the electrons, spins them up to very high energies, which gives you more efficient dissociation and ionization of the gas.
Okay, so almost how like a LINAC or a linear accelerator will work.
Except it's a cyclotron motion. So it has big electromagnets and high-powered microwaves, the right magnetic field for 2.45 gigahertz microwaves, you excite this resonance.
Mm-hmm.
And so That's what creates the high density plasma. So you have a very high density of ions and electrons, which allows the process to go faster because you're depositing and etching, so it's inherently slow as opposed to just depositing. So you want to go to that high density to get the rates up, the throughput up, so it's manufacturable economically, but also that high density, high energy ion bombardment gives you a better film because it tends to remove weakly bound. I never liked the technology because it's more complex, in my opinion. It needs to be the magnetic fields, add cost, and indeed they were struggling. And in parallel, Lam had invented something called transformer coupled plasma to create high density plasma for etching purposes. And that's basically, think of an electric stovetop and you have that coil that heats up. It's the same idea. In fact, the coils looked very similar to that. And you just apply radio frequency energy to that coil and it would inductively couple to the gas and break it down and create an intense plasma with no magnetic field.
Interesting.
Roger Emmerich and company had decided to buy this technology out of Japan rather than trying to develop an organic product with their own. So that there was a lot of infighting over those decisions. I got caught in the middle of that. To make a long story short, again, that product failed. It had a lot of problems, which I underestimated. So I went in there, I did my report, I talked to everybody. I didn't do a good enough job. I should have spent a lot more time in the lab poking my head inside that machine. I would have seen many more problems that I subsequently discovered. But I went back and I said, Lam was way out ahead with this technology because they had bought it from Japan. Applied and Novella Systems at the time were trying to catch up. So we had 4 or 5 customers and they had none. But the machines weren't working very well. So the business was still fairly wide open. So I went in and I wrote a report and I said, they got this problem, this problem, this problem, this problem, but I think it can all be fixed. And yeah, I'm not particularly crazy about ECR, but your TCP effort is 1 to 2 years behind. So it may be superior, but you're going to be too late to market. So kill this and put all your effort over here. They didn't really take my advice. What they did instead was they gave me the responsibility for that product line, but they didn't kill the one that was competing with it inside the company. That continued to confuse customers and dilute resources.
So you have kind of 2 parallel things coming out of the same source. Yeah.
I'm writing a book about this, so I don't want to go into, I could go into a lot more detail, I should say. But so there was a lot of infighting because of this disagreement about strategy. And I got caught in the middle. And the guy I reported to was a champion of the technology I was saying to kill. And I hadn't even talked to him when I had done my study and did my report. And I didn't realize he was fighting with the CEO and the president. There was a lot of bad blood.
A lot of tug of war going on internally.
So that went on for the better part of 2 years. We eventually failed and Applied Materials took all that business. In the interim, the Lam board realized that the company was in trouble. They were spread too thin. They were losing market share in etch for a bunch of different reasons. Their investments in chemical vapor deposition. There was my product line. There was another product line that was purely thermal, no plasma, was also suffering. So they're spending all this money and getting no revenue, not let alone profit from it. And everybody was shorthanded. And the Asian financial crisis hit in '97. Which caused a downturn in the semiconductor business. So they were beginning to lose money. Inventory was out of control. Their operational systems were out of control. Change management was not carefully managed. Most customers were very dissatisfied with the chemical vapor deposition products and increasingly dissatisfied with the plasma etch products. So they brought in a new CEO who came on board officially in August of '97, Jim Bagley, who was previously vice chairman of Applied Materials, came out of Texas Instruments. He ran the Texas Instruments equipment division back when Texas Instruments was vertically integrated. I think he reported into Morris Chang, who's, of course, founded
Yeah.
TSMC.
Oh yeah.
Bagley was a breath of fresh air. I mean, he was a no nonsense guy, able to make very difficult decisions quickly, and a great communicator. So he was able to rally the whole company around a set of core values that might seem obvious. Things like teamwork, mutual trust and respect, honesty and integrity, open communication, achievement, innovation and continuous improvement, and the one that I think is always most important: think, customer, company, individual. A lot of that may seem like motherhood and apple pie, but the difference at Lam was, along with Steve Newberry, who Bagley brought in as COO, I like to say brainwash the whole company. A lot of people take offense to the word brainwash, but we would have very lengthy meetings, initially with the management, but then the management would have it with the individuals in the company. But Steve Newberry himself would bring the management together for half a day to talk about one core value at a time. And there was a definitional statement. What does this value mean? So, for example, I don't remember the exact words, but open communication is really about not being afraid to speak up when something is wrong or you believe your management's making a bad decision, for example.
Yeah.
Honesty and integrity is not, we're not questioning people's honesty and integrity per se, but it's human nature when you've made a mistake to maybe not go out and broadcast it. But if you don't tell people you've made a mistake and other people are building their work or doing their job based on what they think you did,
It just compounds the problem.
It compounds the problem. So they wanted to change that culture in the company, because before that, people would hide bad news.
This culture change in the company, I do want to fast forward over to your final role there at Lam. Your final role there, I believe you were chief technologist, correct?
Yes. Before that, I actually rose to run all etch, and then I ran all products, which were etch products. And after we merged with Novellus, CVD products and clean products. And then in 2017, I became CTO.
And as the CTO role there, this is kind of around the time that you and I got to meet each other. This is now, fast forward, I think it was about another 4 or 5 years after that. The CHIPS initiative is coming out. There's a lot of different buzz around, domestic investment, getting, kind of this shot of insurgents into all of the different portions of the supply chain, right? I want to say kind of two key factors here that we've talked about quite a bit. The one is, there's the way that the semiconductor ecosystem does work today, and there's better ways to do it, right? And we've talked about digital twinning of different items. Describe what your vision is of a digital twinned landscape within the semiconductor manufacturing space.
If you'll permit me, I'd like to provide a little context for that first, because equipment and the processes that run on equipment that are used to make all of the devices in every electronic system that you can think of, they all have chips in them. That's why people have really awakened to the strategic importance of chip technology. Virtually all of that is developed by trial and error, like Edison with his filaments and the light bulb. I mean, we cannot sit down at a computer and design a plasma etcher that will work as predicted to the precision required to make devices on the atomic scale, which is what happens today. So you can design stuff, but in the end, and you build it, in the end, you got to go in the lab and you got to run a plasma and you got to etch wafers and you got to measure the results. And then you got to scratch your head and say, that didn't come out the way I need it to come out. I'm going to change something else. And at that point, you're basing it on human intuition, which is in turn based on people's education and experience. That's where my fundamental work served me very well. But that fundamental work and the modeling I did was never sufficient to allow me to design a reactor or design the process that runs in the reactor. Now, you can design a chip on a computer today, and it'll work pretty much as advertised, assuming you can make it. But you can't design the process by which you make it. That's all still today empirical. Now, and it's not for lack of effort. I mean, over the years, I've started efforts and I've killed efforts where we were trying to do all this with computer-aided design to design reactors and processes. Now, with the advent of artificial intelligence and much more capable computational ability, you can begin, we are combining physics-based models with database models, so-called hybrid models, that now can become much more predictive, much more accurate, with which we can design these processes. And that offers an opportunity to completely revolutionize the speed at which we can develop new solutions and build new chips. New chip technology is largely gated by how long it takes to develop the machines and the processes that run on those machines to make something that's reproducible on an atomic scale across an entire wafer. Every wafer comes out the same.
I mean, look at ASML, right? I mean, they have a whole business on lithography doing
Correct.
exactly that, right?
Right. And lithography is in a much better condition. So you can, the understanding of the optics in a lithographic tool is very, very sophisticated. And you can design a lot of the optics and the whole optical system from first principles and have it work as advertised. Where they get into, where they have the same problem as we do in deposition and etching and cleaning is when the light or the photons actually hit the photoresist and doing chemistry, and then they're kind of in the same ballpark again. It's not well understood, not well enough understood that you can do everything on a computer and design. You are going to do trial and error experiments. I've always had this dream that, or I've always asked the question, why can't we do this why can't we design reactors and processes the way people design chips? And now I believe that's all possible with the new algorithms and the new computational capabilities and the idea that you're going to use a physics-based model which kind of constrains the problem. And the reason you can't use pure physics is there are way too many unknowns, and you can't generate enough data to calibrate the pure physics model. So you use a hybrid approach where you use physics-informed neural networks, for example, or things called neural operators to constrain your database models so that it conforms to the laws of nature, and yet you use as much data as you can to anchor it in reality. And if you can, and we will do this, I think it's only a matter of time, we will create a digital twin, not just of a plasma etcher, but every tool that is in a semiconductor fab, and a digital twin of the processes that run on those tools, and a digital twin of the integrated flow of the wafers through the fab that results in working devices out the other end. If you have that capability in the virtual world, now you can, your pace of innovation accelerates dramatically, and the cost goes way down because you can start to do what-if experiments. What if I change this recipe to that recipe? What if I change this piece of equipment to that piece of equipment? What will happen out the other end? Today, if you do that, you literally change the equipment, you run more wafers, you make more measurements, and by the time you get yield data, it might be 6 months later before you have a data point.
So the way I'm interpreting what you're describing here is there's digital twins that you can do of the chipsets, but taking that idea of a digital twin model and applying it to the laboratory, and not only having each machine, but getting down to the molecular level of what each machine is doing is the ultimate goal. That's kind of the end state. Is that correct?
No, I wouldn't go quite that far. I don't know if you need to get down to a digital twin of what's happening at the molecular level. Think of digital twins as a kind of a layered structure. So yeah, people are trying to model all that. I'm not sure you need to model all that to predict the result of an etch process, or to predict how a transistor is going to work at the end of the line. So, and that's the beauty of the hybrid approach. You know, if you were taking a pure physics approach, you'd kind of think that you need to do all that at the atomic scale, but you don't, because you're going to combine the physics with the data, and the physics.
So like an 80% answer is good enough because you know you're going to get
maybe even less than 80%.
Sure.
And then you're going to use the data to anchor it.
Got it.
And if you use physics informed neural networks or neural operators, it gives you a much better ability to extrapolate and interpolate because you're building in the laws of physics into your model, but still using mostly data to calibrate that model.
You get this in the 80%, I'll use that example, 80% model, and that gets you, down to a 0.002 accuracy, but you spend, 10x time and, a bunch more money to get that 20%, and it goes down to 0.001.
Yeah, in fact,
Yeah.
we set up a, I'll call it a low fidelity digital twin. So it wasn't quantitatively predictive or accurate. It was qualitatively accurate. So the trends, you turn this knob and things go up or down, that was predicted correctly. And the complexity of the model was akin to what people find in the real world. And what we use that virtual environment to measure whether or not this engineer could solve the problem faster than that engineer in a controlled world. You could never do that in the real world. But what we're really trying to do is to test data-based algorithms. So we had data scientists saying, I've got the best algorithm, just give me the data and I'll show it to you. In doing that in the real world is very, very challenging because there's too much noise, too much variability. The virtual world, we just turned the noise off and we created a virtual environment. We gave the same challenge problem to some very accomplished process engineers who do that for a living, and then gave it to data scientists who are expert data scientists but don't have domain knowledge in plasma etching. And the experienced engineers wiped out the data scientists because the algorithms just had no idea where to begin. The solution space was too big. But the experienced engineers had an intuition, so they knew which knobs to turn initially. But then what would happen is they get stuck 80% towards the target. And now they lost their intuition because they had to fine tune multiple knobs in just the right way to get to hit the specification. And so now the data-based algorithms worked extremely well. So what we ended up concluding by doing our experiments in this low fidelity digital twin, let the humans start, let the machines finish. And it was beautiful also because that finishing piece is what frustrates the engineers because they spend 20% of the time solving the problem to 80% accuracy and 80% of their time trying to close that gap. And that 80% of the time is not rewarding because they don't understand what's going on. So it's almost, they have to kind of get lucky almost. Yeah. So it's a great marriage of human machine collaboration. And that's a great example of how a digital twin, a low fidelity digital twin, can give you learning. So what came out of that was a methodology, human machine collaboration, and an internal product, the Lam Research, such that you didn't have to be a data scientist to do the machine learning part. They made it very easy that you run these experiments, you take these results, you just feed it into the algorithm, and it'll do the rest of the optimization.
How far do you think we are as an industry from adopting this kind of methodology?
We're just scratching the surface. It's very early, but things are moving very, very fast. So this is one of my concerns about the state of the United States capabilities in semiconductor technology is these approaches are a digital twin technology, which is much further advanced in aerospace and the automotive industry, as I understand it, is going to change everything. And our competitors around the world are fully aware of all this. And so to me, it's a race. So we need to build the digital twins for our fabs, our factories, before they do. And the first time you build it, it's not going to be very accurate. It gives you an environment to learn in. And every time it fails, it's good news because now you know that didn't work. That model's not right. I need to fix it, and I'm going to make it better.
It's just like the development of AI, right? You look at those video images of AI. There was a lot of failures, and there's still failures.
Right.
but the algorithms are getting better because it's
Exactly.
learning over a period of time.
But you can't get better at a digital twin of the fab if you don't start to build it.
Interesting. So that kind of leads into another piece, right? There's been a lot of investment in the United States, and the CHIPS initiative had some successes, has had some failures as well. But it has identified core aspects of things that need to be, worked on. One of which you sit on the board for, right? Why don't you describe that a little bit?
Well, first of all, having been in the industry for a long, long time, and feeling like nobody cared in America about semiconductors, when I compare it to what's going on particularly in Asia. The attitude in the US was, oh, I can buy it from Asia, so I don't need to do it here. And being in the equipment industry, we were constantly fighting companies in Korea and more recently in China that were being strongly supported by their customers in Korea and China, but also by the governments of Korea and China. And the US government, since the late 80s, early 90s, I mean, there was the Semitech effort, but that petered out after a while, was not really significantly investing in semiconductor technology. A lot of the people in the universities moved on to study other things because they couldn't get money to do basic research, the kind of stuff I did at Bell Labs. Very few people do anymore. They can't get funding for it. And there were no incentives to build fabs in the US. So when the CHIPS and Science Act passed, I was a big supporter. I think it's very good for America. Now, devil's in the details and how you implement it, how you spend that money. And $52 billion, $50 billion to Department of Commerce, $2 billion Department of Defense is not a lot of money. A lot of people think that's a lot of money. Compare it to what China's spending. China's spending more than that every year and has been for some time. So I'm not saying we should do what China does. I think we need to do things better than what China does. But for sure, the US government has a role to play. The strategic importance of integrated circuits cannot be understated. I mean, they're just the foundation of the modern economy.
They're
the
a
foundation
foundational
of everything
technology.
in defense.
Yeah.
Right. So we have to be world leaders, and we have to control the supply chain, which means we have to manufacture in the US. And it's not just manufacturing chips. Semiconductor equipment manufacturing has also moved offshore to some extent because the customers in Korea, for example, and the government in Korea put pressure on equipment companies to build local, right? Why? I mean, there was a quote some years back that the Korean government was asking the Korean chip makers, why are you spending all that money buying equipment from overseas, from America and Europe and Japan? Why aren't we doing that here? Well, the reason they're not doing that, it's really hard. And it's a collaborative effort. But if the Korean chip makers work really closely with Korean equipment makers, those equipment makers will come up that learning curve. So we need to bring chip making back to the US, and we need to strengthen the equipment makers in the US. And the equipment makers have their whole supply chain, RF generators, pumps, gas boxes. And you don't want to be building that stuff thousands of miles away and shipping it across, and you're in different time zones, because all of the development all throughout that supply chain is done in a very collaborative way, in large measure because most of these things are not precisely predictable. You need data and you need people to talk to each other. So the whole ecosystem has to be strengthened in the United States.
Yeah, I think one of the areas that the CHIPS initiative got wrong is there was so much emphasis on building fabrication facilities. That was a big piece, right? But just because you build it doesn't mean that is going to automatically result in a demand to use those sites. You have the increased supply. Where I think there could have been a bigger play is an incentive for those that were actually buying the electronic components and putting funding towards them, and requiring any kind of incentive that went to those that were acquiring the devices to buy domestic. That gave them the opportunity to get some kind of financial contribution back, into their companies, but they would have the fiduciary duty at the board level or the CEO level or whatever it may be to use only domestic manufacturing capabilities. Then the demand would go into each of these different companies that are building the fabs, ultimately the equipment suppliers, and it would be a trickle down type of approach.
I couldn't agree more. In fact, bringing back semiconductor manufacturing in the US is extremely important. Keeping our leadership, because America owns 3 of the top 5 equipment makers that supply the whole industry: Applied Materials, Lam Research, KLA. The other 2 in the top 5 are ASML and the Netherlands, and Tokyo Electron in Japan. So we need to keep it and strengthen that. But we need the consumer electronics. I'd like to see Apple building their products in America. I'd like to see NVIDIA building their products in America.
100%.
Basically, any consumer electronic, I'd like to see built in America. I think the loss of consumer electronics that really kind of hemorrhaged in the 80s and 90s, big loss for America. And it's one reason semiconductor technology increasingly went offshore, because just like there's a lot of collaboration between tool makers and chip makers, and between tool makers and their supply chain, there's a lot of collaboration that's absolutely required between chip makers and their customers. NVIDIA works hand in glove with TSMC, for example. Apple works hand in glove with TSMC and of course, their suppliers in China.
And imagine if the incentive packages were focused on those companies to only use US manufacturing. You wouldn't see fabrication facilities being abandoned or, delayed and the such. They couldn't build them fast enough to keep those large customers happy.
I just finished a book, Apple in China. I don't know if you've seen that, but it's a really good read, and it talks exactly about this. And the essence of that book is that Apple went to China to kind of leverage the capabilities in China, cheap labor. You might even characterize it as slave labor. Because the conditions under which those people work and how they're compensated is pretty appalling. You wouldn't want to reproduce that in the US. So Apple went there, take advantage of low-cost manufacturing, and China made it very easy for them. But in doing so, again, it's a very collaborative business. Apple had to teach those Chinese companies how to build this stuff, what was important, how to control the quality, so forth and so on.
Imagine if that was done domestically.
They're capable of doing it without Apple.
Which is why
who took advantage of whom is the thesis of that book. And in the end, Apple's now in a very precarious position. They're very, very strongly dependent on what's happening in China. How do you get out?
Yeah, they've made their own bed. They got to sleep in it. I mean, we'll see how that kind of works out for the future. But Rick, this was great. Thank you for joining us here on Micro Journeys, and I look forward to following your career in this next chapter, and all the great not only innovations but influence you have into the industry. So thanks a bunch for joining.
Thanks, Dan. Appreciate it.